So now we'll talk about a statistical test that is very closely related to correlation, but you can use it for prediction. Overall, the strategy is called regression, and we're going to start with simple regression. But after we're done with simple regression, we'll talk about what's called multiple regression. And multiple regression is one of the most useful statistical techniques that there are. So it's like used in the business world, it's used by scientists, it's really a powerful technique. But we'll start out with the simple version, right? So you use simple regression when you have one predictor variable and one outcome variable. And the thing that makes it simple is that you have one predictor variable. If you had more than one predictor, you'd be doing multiple regression. And so the outcome variable should be interval or ratio scale of measure. The predictor variable doesn't need to be. It can actually be any scale of measure, and it would work out okay. So, for example, we might think that how much students study will predict exam grades, right? So, students that study more hours for an exam would get better grades. And the null hypothesis here would be that there's nothing happening, right? So in that case, the hour studying is unrelated to or does not predict exam grades. So I'll say studying does not predict exam grades. Right, and usually I would have written this null hypothesis with population parameter symbols. But since I haven't introduced enough material yet for this regression, we're going to come back to what these null hypotheses look like in a little bit. All right, so let's consider an example. Let's say we ask students, 10 of them, how many hours they studied for the exam. So we'll put that on the bottom here. We'll call it X, and this will be the hours studied, the number of hours they studied for the exam. And we'll call this Y, this is the outcome, and this is exam scores. And let's say our results fit our intuitions, right, where the more students studied, the better exam grades they got. So we'll say there's 10 students, right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, so this is a student who studied a lot. Let's say this goes from 0 to 100%, so this is up at 100 here. We'll say the number of hours goes from 0 to 10, right? So this is a student who studied, I don't know, 9.5 hours and got, I don't know, 99, 100%, really did really well on the exam, right? And this person down here studied maybe like 1 hour and failed the exam, right? And so far, this looks a lot like correlation. And we could actually calculate the correlation coefficient of this data. But now we want to switch from just telling if there's a relationship between the two to using regression. And regression is going to do a little bit more than correlation can. Right? So, because it's going to allow us to predict people's scores on exams. So if this is what our data looks like, and we run our data through our statistical program, right, what it's going to do is it's going to tell us the line that best fits through all of that data. Right, this is the best fit line, also known as the regression line, right? And so this line, what we can do with it once we have it is if an 11th student shows up, yeah, and they've studied for 5 hours, given the data that we had from our first 10 students, we can predict that student is going to get about maybe like an 80%. Right? And that's how this regression is going to allow us to predict future observations based on some previous observations that we already have. So you probably remember from high school the equation y equals mx plus b, right? So this is the equation for a line. And in regression, we have a line. And so statisticians actually use this same formula, but of course, that make things more complicated, right? They relabel everything, right? So this, back in the day, this was the slope, right? Remember that was the rise over the run. The rise is like how much the change is this way for each change going across. All right, so that was the slope. And this, that was the intercept. That's where the line crossed over here. All right. But now that we're in statistics, right, I think this might have been algebra, but now what we're going to do is we're going to switch this up a little bit. But the ideas are exactly the same. And call this y hat, cute little hat there, right? So this means it's going to be a predicted value rather than an observed value. It's going to equal a plus bx. So a is now the intercept, right? So whoop, and b is now the slope. But otherwise, they're exactly the same as they used to be, right? So this is still rise over run, and this is still the intercept at the vertical axis, right? And so whenever you do a regression analysis, the result is one of these prediction equations. So you're always, when you do a regression, fitting lines to the data, and that enables you to create this equation and predict future scores. All right, so for this particular data set, we'll say we run our data through regression analysis, and we get our prediction equation. All right, so that's going to be one of these equations, except for we're actually going to have the intercept value and the slope value that fits our observed data. Right, and so for this, it's going to be something like, this is a pretty approximate set of slope and intercept values, so I just eyeballed that based on this, right? And so the way I was able to do that is to find out what the intercept is. That's the value for the exam scores when x equals 0, right? So if you plug 0 in, it doesn't even matter what the slope is because this is all going to be 0. So here, this is all gone. And whatever y is, when x equals 0, that's your intercept. And so here, I guess, that's about 20. Right, so that's how I figured out what the intercept was here. In the slope, remember the slope, right, that's rise over run. Right, so that's how much change in the outcome variable there is per one change in x. All right? But we can actually set like a different value for x. So what I did is I saw that x changes across from 0 to 10. Right? And so I wanted to, just to simplify it, I went across all 10. And for that big change, how much did y change? And it went from about 20 to about 100. So for every 10 change in hours studied, there was 80 change in exam score, right? So 80 divided by 10 is 8. That's where this 8 came from. So if we come back here, what we can see is for somebody that studied 0 hours compared to somebody that studied 1, so x changed by 1, y changed by 8. So that's the rise over the run. 8 divided by 1 is our slope. All right, but you could directly interpret the slope in terms of the actual variables. So if I'm telling my future class how much studying helps, I would say, well, for every hour you study, you're probably going to get about 8 more points on your exam. So if you study about 10 hours, you're probably going to get about 100 on there. That's usually what people did in the past. If you studied, let's say, 8 hours, well, we could just plug that in. Let's see. If you study 8 hours, and it's 8 times 8 plus 20 will be our predicted y value. So that's 64 plus 20. Well, if you study 8 hours, I'm going to predict you probably get about an 84 on the exam, because in the past, that's the kind of scores people got. So this is how you can use simple regression to predict one variable from another. So any new person that comes in, given the data we already have, if they tell us how much they studied, that's their x value, right? That's across the bottom. We could plug that in, and then we could predict their score on the exam. So what makes this line the best fitting line, right? So how does SPSS or whatever's doing your calculations for you know that this is the best line and not one that's a little bit more this way or a little bit more this way? What makes this one the exact best? And what it is this is the line that minimizes the error in predicting y from x, right? So this is the x score, and this is how far off the prediction was for this score. And this is how far off the prediction of the y score was for the x, right? So for each of these are the errors in prediction based on the observed data. So this line is the best line to reduce it. So if you rotate this line, these errors get bigger. They get further. The prediction line gets further away from the point on average. So the best fit line is the one that minimizes the error in prediction of y from x. So it's not just the difference score, because generally half these difference scores are going to be positive and negative, right? And so just like when we did the variance, standard deviation in the past, we're going to square these difference scores, and we're going to end up with a sums of squares here. Right, so this sums of squares is going to be the observed y minus the predicted y value for each score, and we'll square that to turn them all positive. So for this one, for example, right, the actual observed y is where this green is. So maybe that was 98. And the predicted y is wherever this line is. So that looks like it might be 100. So in that case, you would take 98 minus 100 and square them, right? And you do that for each 10 people, for each 10 observations. You add them all up, and that's the sums of squares error. This is the error in prediction. This is the sums of squares associated with error. This is the inaccuracy in our regression equations predictions of y scores from x scores. So the best fit line minimizes the sums of squares error. Right, so the regression line is the best line for predicting. It's the one that has the least amount of error in predicting scores based on the observed scores. In regression, there's an overall amount of sums of squares, a sums of squares total, just like there was for like ANOVA or even calculating the variance, right? And so the sums of squares total, this is how much variation there is in y. Right, so this is how much error there is in predicting y, and sums of squares total. This is the total amount of variation in y that could be explained by x, right? And so the sums of squares total for y is just y, all 10 y scores, right, minus the average y score squared. So this is just the regular old, that's not an x, that's a y. This is the regular old sums of squares, right? And that just tells us how much variation there is across y scores, just the total amount of variation that could possibly be explained. And now that we have these two types of sums of squares, what we can calculate is how much variation in the outcome variable is explained by this line here, right? And we'll call that the sums of squares regression, and it's equal to the sums of squares total, all the variation that could be explained, minus the sums of squares error, the variation in y that's still unexplained, right? So this will tell us, this here will tell us how much our regression explains the variation in y. And so if we actually calculate the sums of squares regression divided by the sums of squares total, this is how much of all the variation that exists in the outcome variable, how much of that variation, what percent of it or proportion is explained by the line. And so if your sums of square, if your regression explained all the variation in y, these would be the same. It'd be something, I don't know, we'll say 500 divided by 500. All of it's explained. In that case, you get a 1. A 1 is the maximum value. If the line doesn't fit at all, if your predictor doesn't explain any of your outcome variable, if these two variables are uncorrelated, then your sums of squares error and sums of squares total are going to be the same, and your sums of squares regression is going to be 0. And in that case, the worst case scenario, the result of this formula would be a 0. Right? And so this is called r squared. And if you remember from ANOVA, we had something called eta squared. And eta squared and r squared are exactly the same, conceptually. They're both the sums of squares total on the bottom, and on the top is the sums of squares explained by the relevant variable. And in this case, it's the number of hours studied. So remember, eta squared and r squared, they're both the same. They both have a maximum of 1 if the variable explains all the variation in the outcome variable, or a value of 0 if they don't explain the outcome variable at all. And so for simple regression, the r squared is that's the effect size. So we've been working with what are called unstandardized coefficients. Right, so we said that the predicted value of y equals the intercept on the vertical axis, the y-intercept, plus the slope times your x value. And for this example, we said that looked like that. Right, so here we said for this, a equals 20 and b equals 8. So next I want to talk about something called standardized coefficients. Standardized. And this might make you think standard deviations, and if so, that's good because standard deviations are involved. But really these standardized coefficients are another way of looking at this exact same equation, this exact same data, but it's a little bit more a general approach, I would say. Right, so for these standardized coefficients, you don't actually predict the y-score. Instead, you predict the z-score for y. So what you actually do for these standardized coefficients is you do a z-score transformation on all of the exam scores, a z-score transformation on all of your predictor variable scores, how many hours you studied, and you run the regression on those standardized, those z-score transformed variables. And so over here, we're going to have, for exam scores, it's going to be, we'll say, z for exam scores. Down here, it's going to be the z-scores for the number of hours you studied. Right, and so remember, a z-score is just the actual score minus the mean of that variable divided by the standard deviation for that variable, right? So the mean score for hours studied, right, would have a z-score of 0 because it would be the same as the mean. Right, so this would be the formula to change these raw hours studied into the z-scores for x, right? And for y, we take each y-score, subtract from it the mean of the y divided by the standard deviation of the y, right? So these are the familiar z-score formula that we've been working with all semester. But now what we're doing is we're transforming our predictor variable and our outcome variable before we're running our regression. And if you do that, what we're predicting now is a z-score for y. And you actually don't have, well, there's always an intercept, but in this case, the intercept, once you've done a z-score transformation, the intercept is always 0, so that just drops out of the equation. And b is now written as beta. So this is the first case where the Greek letter doesn't refer to a population parameter, and the Latin letter to a sample statistic. Beta refers to the standardized coefficient, b to the unstandardized coefficient. All right, so here we have predicting the z-score for y with our standardized coefficient, and we need to plug in, rather than a raw x value, the z-score for our x value. So it's a slightly simplified formula, right? And so now what this beta is, right, is the rise over the run still. So it's the change in the z-score for y for each change in the z-score for x. So if you compare, so if this is 0, right, the mean of x, if you go up 1 standard deviation here, how many standard deviations do you go up for your y? And in this case, my guess is it's going to be about, beta is going to be about 0.9. And if these two are perfectly correlated, if there is no error in this prediction at all, beta is 1. And notice if this were going down, if it were a negative correlation, and if there was no error in the prediction there, then beta would be -1. All right, so a perfect prediction in a negative way, a negative association, -1, perfect prediction in the positive direction as a +1. So that's exactly the same limits as a correlation coefficient has. And in fact, for simple regression only, your beta is the same as the correlation coefficient. So you can use, for simple regression, you can run a simple regression on 2 variables. SPSS will tell you what the beta is, and that beta is exactly the same as if you did those exact same variables and did the correlation, right? So the correlation equals beta for simple regression. They're exactly the same as one another. All right, so I drew the standardized regression coefficient equation, the standardized regression equation, but I didn't fill it in, so I'm going to do that here. This should actually be the predicted value for y. So here we got the z-score for the predicted value y equals, now we actually have our beta, so that's 0.9, and this is the x, right? So if we want to figure out a predicted z-score for exam scores, we plug in a z-score for the number of hours studied. And so when you're actually doing prediction, you almost always use this formula because you're interested in exam scores. That's the interpretable unit for this kind of data. But to get a better sense of how strongly related 2 variables are, you often use a beta, because correlation coefficients are something that people tend to understand pretty well. They have a maximum of 1, minimum of -1, 0 is unrelated. So correlation coefficients are nice, they're intuitive, people get a pretty good sense of what those mean. So for interpreting the relationship between these 2 variables, the beta, or an R, is really nice. Right? So notice this constraint, the +1 to the -1 for the correlation coefficient, or beta equivalently, right? That makes it intuitive. When you think about a B is not all that intuitive. So if you do 10 different regressions on 10 different pairs of variables, B could vary widely. So if you're working with numbers that are like 0.0015 is like, if it's like reaction time in milliseconds, your B value could be something like you know, 0.00023. It's a super tiny number. Or if you're working in incomes, right, your B value could be a huge number. It could be like 1,000. So B values, there's no limit on their range. It's just determined by whatever the variables are like that you're using. That makes them hard to compare across 10 different pairs of analysis, like the relationship across 10 different variable pairs, right? Because sometimes they could be, a b could be a tiny number, sometimes a b could be a huge number. But for all of those 10 simple regressions, if you look at the beta, you'll be able to directly compare them. And whichever ones have the strongest absolute value, right, the closest to 1 or -1, those are the variables who have the strongest relationship. All right, so betas, or r's equivalently for simple regression, are much easier to interpret and compare across analyses than b values are. So that's one thing that makes these standardized coefficients really useful, is you can compare apples to oranges. All right, so beta values, standardized coefficients, and b values, unstandardized coefficients, are mathematically related to each other, like directly, and you can actually transform one into the other pretty easily. And if you remember what a beta is, it's for each change, the amount of change in the z-score for the y variable, the outcome variable, for each change in the z-score for the predictor variable, right? So these are z-scores, right? And b values are in raw scores. And remember, a z-score, if I just kind of put the formula in here, right, it's y minus the mean of y divided by the standard deviation of y. That's not kind of on the top. And on the bottom, it's x minus the mean of x divided by the standard deviation of x. Right, so if we want to turn these from standard deviation units back into hours and scores, we need to get rid of these standard deviations on the bottom. So what you can do is you can take a b value, or sorry, you can take a beta value and multiply it by the standard deviation of x divided by the standard deviation of y. And so what that does is it basically cancels out those two, leaving you with the original units that you had before. And so if you just take a beta value and multiply it by the ratio of those two standard deviations, you get your b value back. You get your unstandardized coefficient back. You go from units of standard deviation to the original units, scores per hour studied. So this equals b. So you can transform these pretty easily back and forth, although in practice you wouldn't need to do it. Because if you do a simple regression in any statistical program like SPSS, it's going to tell you what A is, it's going to tell you what B is, and it's going to tell you what your beta is. Those are just part of the outputs. So you don't actually need to mathematically transform these, because SPSS will tell you all of them automatically. It's a default part of the output of the statistical programs that we use. All right, so next I want to talk about some limitations. I'm calling that some limitations of simple regression. I'll talk about 3. The first one is that with regular regression, the way I've described it, you can only detect linear relationships amongst your variables, right? So if you can fit a straight line, that's all it can do. It can't handle the kind of relationship you get when you have performance and arousal. For example, right here, people that are under-aroused don't perform well, over-aroused don't perform well, but there's an optimal level of arousal. So the basic version of regression can't handle this, although there's more advanced techniques where you can transform these variables before you do the regression, and you can detect nonlinear relationships with that, but not for the version that we've talked about here. Another limitation is that just because one variable predicts another doesn't mean the predictor variable is causing a change in your outcome variable. This is the same exact concern we talked about for correlations. And really, you could think about simple regression as a type of correlation, or you could think of correlation as a type of simple regression, because ultimately they're the same thing. When you have a standardized beta and a correlation coefficient, are the exact same thing, right? So in some ways, they like directly change into one another. And so you don't know if A is causing B, B is causing A, or if a third variable is causing the change in both. And the third thing that I'm going to call limitation is called regression to the mean. And first I'll illustrate it, and then I'll tell just a little bit about the history of this idea, right? Because this is why this technique is called regression, right? So it's kind of important to understand why it's called a regression to understand what's going on here. So well, let's consider a situation here where there's a correlation between two variables. It's a very strong positive correlation, correlated 0.85. That means the beta between the two variables is 0.85, right? And here's the prediction equation for standardized coefficients, right? So all we're going to do is put our beta 0.85 in here, right? And then we can plug in whatever we want for our z-score for x, and that'll give us our z-score predicted for y, right? So if we put a 2 in here, 2 times 0.85 is 1.7, right? If you put a 1, if you put a 1 in here, right, then you get 0.85. Put a 0, there's nothing over here, you get a 0 for the predicted y value. And if you put a -1 in, you get a -0.85, -2, you get -0.17, right? So nothing too surprising here, but what I want to point out is that the predictor variable is further from its own mean than is the predicted value, right? So this score here is 2 standard deviations away from the mean, whereas this one is only 1.7 standard deviations away. So the outcome variable that's being predicted is always closer to the mean than the predictor variable. And so that's called regressing towards the mean. And historically, this was identified in actual data by the person who invented the correlation, the first version of it anyway, who was Sir Francis Galton, Charles Darwin's cousin. And what he was looking at is IQ in families, so like parents and kids. And what he found out is if he used parents' IQ to predict their kids' IQ, if the parents were really extreme, really intelligent or really unintelligent, either way, their kids tended to be closer to the average intelligence. So it turns out that this regression to the mean, not only does it happen when we use our equation, but it actually is a phenomenon that happens in the real world, where if you use more extreme predictors, you pretty much always get less extreme actual outcomes in the world. So if 2 tall people have a kid, or have a bunch of kids, those kids will tend to be shorter than the 2 parents. Or if 2 really short people have kids, their kids on average will be taller than the parents. They'll be towards the average of the population. So extreme predictors end up having less extreme outcomes, unless you have a perfect correlation of 1, which in practice doesn't really happen.